So in this example, we're asked to find a potential function for, excuse me, I've got a yawn. Oh my. There's no one here to share it with either. Uh, I want to find a potential function for this particular vector field. And I want to walk you through this process. It's a process you'll need to know how to do. It pops up a lot throughout this chapter. So let's begin. So first off, if I'm telling you to find a potential function, you can assume that your function is conservative, which means that it's the gradient of something. So we are going to go ahead and assume that we can write our big F as the gradient of little f, right? That's if we can't do that, there is no potential function. And so our goal is to find this little f. Well, let's realize, though, that when I write this as the gradient of little f, then I can think about big F as f partial x, comma, f partial y, little f partial z. And so I'm saying this vector field right here, let's copy it and put it right here. This vector field right here is equal to the gradient. It's f partial x, f partial y, f partial z. And so I'm going to equate some things. I can now see that f partial x, little f partial x is yz. And I can see that little f partial y is xz. And I can see that little f partial z is xy. Now I'm about to do a process, and I typically start with f partial x and just work my way around. You can actually start with any one of these three. It doesn't matter which one you pick. It's the same process. So try very hard to learn the process here and realize that it doesn't matter which one you start with. So I'm going to start right here. When I take my scalar function little f, and I take its derivative with respect to x, I get yz. And so that means if I integrate f partial x, if I integrate that with respect to x, I'm going to get my scalar function back. So I now know that I can write f of xyz as integrate this with respect to x, and you get xyz. And you're probably thinking, well, surely it's not that simple. It's not. I'm integrating with respect to x, and so I get a constant out, but the constant can involve variables of y and z. Stop for a minute and think with me. If I go from here backwards and I compute f partial x of this expression, if this expression g only has y's and z's and constants in it, then when I take the derivative of this part with respect to x, I get 0. It's gone. And the derivative of this part with respect to x is just yz. So that's where we are. Now you have to figure out what g is. That's the fun. And so you say, okay, well, now I'm going to go ahead and I'm going to compute f partial y myself from our formula that we came up with. So I'm going to take partial y of this stuff, and I get what? I get an xz plus, who knows what I have here, but it's just g partial y. All right, so g partial y, and g partial y is going to involve some y and z. I'm not going to write that. I'm just going to say g partial y. But on the other hand, you need to realize that we already know what f partial y is. F partial y is xz. And so this tells you something. If this, xz plus g partial y equals xz, then you know that g partial y equals 0. And that means that when we're back here with our g of yz, that means there were no y's there. If there was a y in g of yz, then g partial y would not be 0. So I know that g is really just a function of, at most, z. And so now I'm going to rewrite my f. I now know that something more about f of xyz. It's xyz plus my function g, which is no longer, there's a function of y. It's just a function of z. Maybe it's just constant. We don't know. And now I play the same game again. I'm going to compute f partial z, and I get xy plus g prime of z. But I know what f partial z is. F partial z is xy. And so, again, I can see that g prime of z is, in fact, 0. So that means there's no z's in g of z either. this g function is turning out to be rather lame, and that's good. It makes it easier for us. So now we know that f of xyz is xyz plus some constant c. So I just have to pick one of some constant. I just need one potential function. So we can point out that f of xyz equals xyz is a potential function for our big F equals to whatever it was. Let's just copy it. I don't feel like rewriting it. So I wish that you guys all had iPads and you could do this with me. It's pretty nice. So we'll just do that. Whoops. So that's we're done now. We found a potential function. You can always check this. You can check yourself that the gradient of little f is indeed what we are saying it is. I won't bother with that, but I would encourage you to. So that's all the material from 13.1. No homework from this section. Don't worry, you'll have plenty of opportunities to find potential functions and those kinds of things in the future upcoming sections. So we're going to go ahead and dive right into section 13.2.